In this lesson, we're going to compare ionic and covalent bonding. To begin, we're going to look at this chart, and I'd like for you to copy this chart into your notes. You may want to just pause the video, copy this chart down, and then pick back up when you've got it copied down. For ionic bonds, electrons are transferred. For covalent bonds, electrons are shared. With ionic bonds, they consist of a metal plus a nonmetal. With covalent bonds, or covalent compounds, they're going to consist of two or more nonmetals. Naming is in a box here because naming is one of the big differences between ionic and covalent. When naming ionic compounds, you do not use prefixes, and you want to consider your transition metals. If you have a transition metal, it's going to need a Roman numeral to indicate its charge. Covalent compounds, they do use prefixes. Those prefixes like mono, di, tri, tetra, penta, and all of those. Next, ionic compounds exist as crystals with thousands of charged ions. Covalent compounds exist as independent molecules, and that's why they're sometimes called molecular compounds instead of covalent compounds. Ionic compounds are always solid at room temperature. Covalent compounds may be solid, liquid, or gas at room temperature. And finally, ionic compounds conduct electricity when dissolved in water, and covalent compounds do not conduct electricity when dissolved in water. So back to the naming part, we're going to practice the difference between naming ionic and covalent and how to know which naming process you're supposed to use. So we're going to classify each of the following as ionic or covalent, and then we're going to name them using the correct way to name these. First of all, to decide if it's ionic or covalent, look at the elements that make it up. If it consists of a metal plus a nonmetal, we know it's ionic. So for this first one, it consists of Na and F. I'll find Na and F on my periodic table down here. There's Na, it's a metal. F is a nonmetal. So if you have metal plus nonmetal, you know that it is ionic. If it's ionic, I don't have to worry about prefixes. I do need to ask myself if there's a transition metal though. Na is not a transition metal. The transition metals are found in green on this particular periodic table. Plus, Pb and Sn act like them too. So those are my transition metals and they're not present here. So this one is really easy to name, simply sodium fluoride. You do not use a prefix for this one because it's not covalent. All right, my next question is NF2. For NF2, I've got N and F. Let's find those on this periodic table. N's way over here, it's a nonmetal. F is way over there, it's a nonmetal. If I've got two or more nonmetals, it's covalent, and I do need prefixes. So since I do need prefixes, the first element is just nitrogen. If there's just one of the first one, you don't need to say mono, so we'll just say nitrogen for N, and there's two fluorides. That means we have to say difluoride. So look at the difference between these first two. The one in purple, NaF2, was ionic, so it didn't need the prefix for 2. The second one was covalent, so it did need the prefix for 2. Next we've got CuO, number 3. CuO. Let's find those on the periodic table. There's Cu. There's O. Alright, so here we do have a metal plus a nonmetal. It's ionic. And most importantly, we have a transition metal. If you have a transition metal, you're going to have to use a Roman numeral to indicate the charge. To figure out the charge, just draw the formula unit. Find the charge of the other element. In this case, oxygen has a charge of 2-. If that's 2- and there's just one copper, we know the copper must be 2 positive. And so that's how I know I'm going to put a Roman numeral 2 after copper in the name of this one. I'll call it copper, Roman numeral 2, oxide. If you have a transition metal like copper, you're going to show me its charge with a Roman numeral. You'll figure out its charge by thinking about what it's bonded to and how you're going to get that neutral formula for it. Next we've got C2O2. Carbon's over here, number 6. Oxygen's over here, number 8. These are both nonmetals, so therefore we're going to have a covalent compound again, and we're going to use prefixes. The prefix for 2 is di, so I'll have dicarbon. Prefix for 4 is tetra, so tetraoxide, or tetroxide when you blend it. So this is dicarbon tetroxide. If you told me tetraoxide, I would take it, but you actually drop the A so that those vowels blend together there. Last one is MgCO3. When you have more than 2 elements, in this case we have 3 elements, Mg, C, and O, this means that you must have a polyatomic ion somewhere. And in this case, there's our polyatomic ion that we're dealing with. So when you have more than 2 elements, I want you to get your list of polyatomic ions out and find your polyatomic ion. In this case, it's CO3, which is carbonate. If you have a polyatomic ion, you know for sure that it's an ionic compound because it's a polyatomic ion. Also, you can prove that because Mg is a metal and C and O are both nonmetals. So once again, we have an ionic compound. And for naming these, they don't need prefixes or anything. We're just going to name it magnesium. And then we see that carbonate is the polyatomic ion there. Okay, so ask yourself, is it a metal plus nonmetal or 2 or more nonmetals? If it's a metal plus a nonmetal, you do not use prefixes. If it's 2 or more nonmetals, you do use prefixes. If you have a transition metal, like in number 3, you need to indicate its charge with a Roman numeral. And if you have more than 2 elements, like in number 5, we had 3 elements, you know that you've got a polyatomic ion involved, so you need to look up your polyatomic ion. The next thing we're going to talk about is empirical and molecular formulas. Empirical formula is the formula written as the simplest ratio. Ionic compounds are always in empirical formula style. Let's add that. Ionic compounds always use empirical formula. They're always in the simplest ratio. Molecular formulas, sometimes they're the simplest ratio and sometimes they're not. But it's the formula that describes how many atoms of each element exist in a single molecule. Now we're going to practice writing empirical formulas. Here we have 3 different formulas, and we're going to practice writing their empirical formula. The first one says C8H10N2O4. You may notice that all of the subscripts are even. If all the subscripts are divisible by some number, in this case they're all divisible by 2, we'll divide them by 2, and that's going to give us our simplest ratio. So 8 divided by 2 is 4, so I'm going to say C4. Okay, 10 divided by 2 is 5, so I'll say H5. Four divided by 2 is 2, so it's going to be N2. And then for oxygen, 2 divided by 2 is still 1, so I'll just say O or O1, but you don't need the 1. It's an understood 1. So there's my empirical formula. It's the simplest ratio. Now sometimes you'll have a compound like number 2, C25H4. Those aren't divisible by anything. They don't have a common factor. All right, 25 can't be divided by 2 or 4. 4 can't be divided by 5 or anything like that. And if that's the case, you're already in the simplest ratio. So you already have the empirical formula. So you can just rewrite it. It's already the simplest ratio. We look at our next one, N2O3. Again, that's already the simplest ratio. You can't reduce it any more than that. So the molecular formula is the empirical formula. Let's do one more just to practice this one more time. What if I had another one that was N12O15? Do 12 and 15 have a common factor? Yes, they do. They're both divisible by 3. So to get this one into its empirical formula, I'll say N12 divided by 3, O15 divided by 3. So that makes N4H5. There's my empirical formula for that one. You simply reduce it to the simplest ratio. And now the last thing we're going to talk about today are the diatomic elements. And this is a review. We've talked about these already. But the diatomic elements means that they're found in pairs in nature. It means they're made of 2 atoms. They're still pure elements. They're just always found bonded to one another. Most of the diatomics do single bonds, like hydrogen, single bonded to a hydrogen. Fluorine is single bonded to a fluorine. And that gives them their octet for fluorine. Same thing with something like bromine. But there are 2 of the diatomics, oxygen and nitrogen, that do multiple bonds to form their diatomics. Oxygen makes double bonds, and nitrogen makes triple bonds when it's found in nature as the diatomics, while all the others are going to do single bonds. And that's our lesson for today.